Hello, everyone. Thank you for joining me today. I'm Francesco Zoffoli, and today we are going to explore how to automatically process your operations in bulk with coroutines. Let me give you a brief introduction. I'm a professional software engineer. I'm passionate about C++, and I use it throughout my career. I'm currently building monitoring systems at Facebook, and I'm the author of the C++ Fundamentals book published by Pact. But let's jump into the presentation. Today, we look at the problem, which is bulk operations are important, but they impact the readability and the maintainability of the code. We'll see an idea to overcome the drawbacks while keeping the benefits. We'll also jump into the introduction to coroutines as they've been introduced in C++20. And then we'll see how we can implement our idea using the coroutines to solve the problems that we identified at the start. Here, we're going to implement the solution from scratch, and there's going to be plenty of code. Finally, we'll see how our implementation performs compared to a manual solution. The takeaway is that if you know coroutines already, hopefully you're going to see a cool approach to using them. And if you don't know coroutines, you're going to learn and get an intuition about how they work in C++20. Feel free to leave your question in the Q&A chat, and I'll make sure to stop regularly to answer them. If you prefer to follow along looking at the code on GitHub, you can use the link here to get to the source. Otherwise, the code is going to be shown on the slides anyway. Now, let's get started. So let's look at the problem. Bulk operations tend to be better than single operation. But what is a bulk operation? There's no specific definition, but in general, they mean processing multiple actions or data, a batch, at once. And because of this, are also called batching. You'll hear both in the talk, and they mean the same thing. Example of bulk operations can be networking, file I/O, memory allocation, GPU draw call. There are many different kinds, but in general, they have a common property. Their cost is a fixed cost plus a part which is proportional on the number of operations on data being processed. An example can be the network latency, while the round trip might take longer than the actual data transfer. Another example is a write to the disk, where the disk seek might take longer than actually writing the data. And similarly, for example, in a database, scanning a table, loading the data into memory might take longer than actually every condition that needs to be checked per row. Each field has different real case scenarios. An example from my background is producing many small events into a queue, reduced its throughput compared to putting batches of events. What are some examples that you benefit from batching? Share them in the live chat if you have any. But we mentioned better. What is better? It is multiple aspects, actually. It could be throughput, it could be latency, but there are also other considerations. For example, if you're using an external API, you might have rate limits, or maybe you're paying a cost for every call that you're making. Different properties are important in different situations. And what you optimize for depends on your context, but batching can be helpful in many situations. For the rest of this presentation, we'll look at a concrete use case. We will want to send a notification to a group of users respecting their preferences. This is so that we have a concrete problem to solve. In this problem, we are going to have two bulk operations. One is fetching the preferences of the users, and the other is sending notifications. Here, we can see the signature. We have the getPreferences function, which takes a vector of user IDs and return a vector of user preferences. And then we have a sendNotification function, which gets the email addresses where we need to send the notification and a vector of Boolean, which says whether the notification was successfully sent or not. If we were to implement this code by hand for every user, we would simply use a for loop over every user and then call the function with a vector with a single user and get a single response of the user preference. Then we could check the preference, whether the user wants to be notified or not. And if they want to, we are going to call our batch call again with a vector with a single element, which is the notification email of the user. This is very simple to read and basically express what we want to do, but it's not using batching. And we said that batching is important. So let's rewrite the code using batching. Here, we are going to start with a vector of user's ID, and then we can use the std library algorithm transform to extract the user ID from the users and put it back into the user IDs. At this point, we have a vector of user IDs, and we can call getUserPreferences with all the IDs to get the preferences. Next, we need to make sure to remove the users that don't want to be notified. So we are going to use removeIf, and then check the users that don't want to be notified so that we remove them from the vector. Finally, we will need to extract the email we want to send the notifications to. So we'll start again with a vector of emails and use transform to get the notification email property of the preferences. Then we are going to send the notification with the emails. Once put all together, this is the resulting code. What we can see is that the code is very different. It requires more effort to read and understand what was the idea behind the logic. It uses extra memory because we have multiple vectors which are kept alive for the duration of the function, unless you explicitly call clear. And also, you cannot use const on the vectors because the algorithm are going to modify the vectors after they've been created. But is this a complexity actually needed? Well, let's run a simulation. In this simulation, we are going to have a 10 millisecond delay for each call to the function, and this simulates the network latency. Then we are going to have a 50 microsecond delay for each item processed, and this is for the operation that need to be happening per item. We are going to send notification to 100 users, and only 50 of them wants to receive the email. And this is the result of the benchmark, where we see almost a 50 times difference between our manual solution and the no batching solution. But this result is obvious. The cost is extremely high in calling a single function. So it's no surprise that manual batching outperforms no batching by a lot. But this kind of situation is actually not very different from many that happen in real-world scenarios. I think there's no questions so far, so I'll continue.
No questions indeed.
So let's look at the idea. Can we keep the readability of the first version and the batching behavior of the second one? What if we could gather all the parameters that we passed to the functions before actually running the functions? So imagine we have 4 users. As we execute the for loop, the getUserPreferences is going to be called 4 times, each time with a different user ID. We want to gather all these parameters before full execution of the rest of the body. How can we do that? Well, we can imagine that the body of the for loop is actually a function, and each user gets its own separate execution of the function. Now, imagine we could intercept the call to one of the function and suspend execution. At that point, we could store the argument to the call and then execute the function for the next user. At the end, we would have gathered all of the arguments passed to the function. Let's see it more visually how it would look like. So in this diagram, the red arrow is where is the current execution, and the blue arrow is where the execution suspended. We are going to start from the first line of the first user. Initially, we are going to get the user ID and store it inside the batch and move to the next user. Again, here, we are going to store the user ID of the user and suspend the execution, and then continue for the next user again, where we are going to gather the user ID again. We are going to suspend, and then at this point, we have all the user IDs, so we can perform our operation and get the preferences. At this point, we have the results, so we can resume the execution for the first user and provide back the preference. And from here, the execution can continue. And it continues until it reaches another suspension point, which is the send notification function. Here, we could store the preference email again and suspend and continue to the next user. And similarly, we are going to again put the preferences and continue with the execution until suspension point, and the same for user 3. With this, in this way, we gathered all the user IDs and we managed to execute the batch operation. So the idea is to execute it until a batch operation is reached. We are going to record the argument and stop the execution. If not enough arguments, we are going to continue executing functions to gather them. Otherwise, we are going to execute the batch operation and we are going to resume the stopped operations with the results that we gathered. What do we need to implement this? Well, we need to be able to suspend the execution and to resume the execution. And coroutines allow us exactly to do that. Continue.
No questions yet.
Perfect. So let's look at coroutines. What is a coroutine? A coroutine is a resumable function. It starts in an executing state, and then it can be suspended and resumed. This cycle can happen multiple times, and at the end, somehow, the function is going to terminate. Coroutines have been added in C++20, and the standard defines several customization points, which are called by the compiler. Implementing these functions, the user defines how the coroutines work. In this section, we're going to see how the customization points added by the standard work. And in the next section, we are going to implement them to achieve our goal. But how does a coroutine look like? Well, it's a normal function. It has a name, it has a return type, it has a body, but it can use some special keywords and has some extra requirements. To be a coroutine, a function must call at least one of coawait, coyield, or coreturn. And it must have a return type which satisfies the requirements for coroutines. What are these requirements for the return type? One is that it must contain a nested type called promise type. And the second one is that the promise type must implement several functions. There's no requirement on the name of the classes. You'll typically see them called task, or when implementing the awaitable callbacks, it's going to be called awaitable. The implementation of the function defines how the coroutine behaves. The compiler is going to transform the code to call these functions automatically. It's quite similar to the for range loop. Let's look how the body is rewritten. The body of the coroutine is going to instantiate the promise type, and then it's going to call coawait on the initial suspend method. Then, inside the try, the function body, which we actually write in the function, is going to be executed. And if any exception is caught, an end of the exception is going to be called. In the end, final suspend is going to be called and coawaited. Now we'll see every single call individually.
We have a question, if you have a moment.
Yeah, perfect.
We have a question from Zishan, which is in C++20, my understanding is that the coroutines are essentially stackless. Does the standard define symmetric versus asymmetric coroutines? Would you have examples of each?
The coroutines are stackless, that's correct. For the symmetric and asymmetric, I assume we are talking about the transfer when changing the resumption of the coroutines. And we are going to see how this is done with, actually, we are going to implement initially the asymmetric and then the symmetric transfer in the implementation part.
Thank you.
Cool. So let's build a valid coroutine type. As we said, we are going to call our type task and needs to have an inner type, which is called promise type. Okay. When my coro is invoked, the compiler will create the coroutine state, instantiate the task promise type, and then call getReturnObject. GetReturnObject is a function which returns the object that is going to be returned to the coroutine caller once the coroutine gives control back. After that, the compiler is going to call initial suspend and is going to run call coawait on the result. But what happens when coawait awaitable happens? Let's look at an example of implementing an awaitable struct. The compiler inserts several calls to the awaitable methods. First is going to call awaitReady. AwaitReady returns a Boolean. And if the result is true, it means it immediately resumes the coroutine. So the coroutine does not stop. But if it's false instead, it's going to suspend the coroutine. After suspending the coroutine, the compiler is going to call await suspend with the coroutine handle to the current coroutine. It's the responsibility of this method, most commonly, to schedule the coroutine to be resumed again. We are going to see what this means later on. Once it's resumed, the compiler is going to call await resume. This is going to return an object, and the co-await expression evaluates to this object. After this, the execution is going to continue in the coroutine body from where it left. We mentioned the coroutine handle a couple of times. What is a coroutine handle? A handle is a non-owning pointer which controls the coroutine. The coroutine handle methods are two. It has a resume, which resumes the associated coroutine which has been suspended, and destroy, which destroys the associated coroutine. Destroy can be called even if the coroutine has not completed. As long as it's in suspended state, it can be destroyed. Coroutine handle is a template, so you can provide the type of the promise type it points to. When this is done, it provides some additional methods. It has a promise type, which returns a reference to the associated promise. And it has a from promise function, which is a static function, which creates a handle from a promise reference. Let's see how all of these works together. In this case, the coroutine calls co-await on an awaitable. It's going to call await ready, and this is going to return true. Since the awaitable is ready, the compiler is not going to suspend the coroutine, and it's going to call await resume immediately. This is going to return a value, and the coroutine is going to continue with this value. In the second example that we are going to call await ready, and the awaitable is going to return false. At this point, the compiler is going to suspend the coroutine and call await suspend with the handle to the coroutine. At this point, more commonly, the awaitable will schedule an operation on some kind of executor. Later on, once the operation is completed, the executor is going to use the handle to call resume. This is going to resume the coroutine, which then is going to call await resume on the awaitable. And the awaitable is going to provide the result back. Now, let's go back to our promise type. That's how we left it. Do you remember that we're calling co-await on the awaitable returned by initial suspend? This allows the coroutine to suspend before it starts executing. Once resumed, it will start from the beginning of the function body. This is called a lazy coroutine, and the task type is going to be immediately returned but to the caller of the coroutine. If the awaitable instead doesn't suspend, the function body starts executing immediately. This is called an eager coroutine. The task is going to be returned to the caller once the coroutine suspends or once it terminates.
We have another question.
Yeah.
How does the compiler know to call await suspend, or is that co-await? Asked by Jeff Erickson.
This is specified by the standard. You can see how the coroutine is being rewritten, which is similar to what I showed earlier. And when there's a co-await expression, the compiler knows that it needs to call await ready, and if the result is false, it's going to suspend the coroutine. I hope this answers the question.
Thank you.
So let's see how we can return values from a promise type. If the compiler is going to find the return with an expression, it's going to call return value passing the expression to the function. Otherwise, if it just finds return, it's going to compile this to return void, to an invocation to return void. We can also handle uncode exceptions. And uncode exceptions are exceptions which bubble up beyond the body of the function. And when this happens, the compiler is going to call uncode exception. And finally, the compiler is going to call final suspend and co-await the result, similar to the how it did for the initial suspend. Now we have everything we need to implement the idea. I'll skip because I see there are no questions. Let's look into implementing the idea. We learned how to suspend execution and how to resume the execution. So what we want to do is we want to transform the loop body of the for loop that we saw earlier into a coroutine. We want then to use a wait to interrupt the execution and store the argument to the call. Then we are going to execute the batch when it's ready. And we are going to resume the execution with the result. And here we can see how we want to change our code. Initially, we had our for loop over the users, and we are changing here by extracting the body and putting it inside the function. The function is going to be called send email, and it's going to return a task that we will implement in the next section. Then we are going to use coawait in our suspension points, which are the two batch operations that we want to perform: get user preference and send notifications. Also, remember that our function were taking vectors. So we were passing with a single vector and accessing the item inside the vector. In our new version, we just want to give a single ID and return a single preference.
Two questions, if you have a moment.
Yeah.
The first one is, are all of the coroutines you use inlined by Jaroszewski?
The optimization depends very much from the compiler. If it has visibility, it can inline. I think this also tends to be a question about memory allocation. Typically, when asking about inline is whether the allocation is going to be removed and the coroutine is going to only live in the stack. The compilers can do that in specific situation. This is not one of them. We can dive more into it later on, but the main reason is that we don't have a single coroutine. We have multiple coroutines concurrently executing. So the compiler cannot remove the allocation for the first coroutine. But when chaining coroutines, the compiler are quite good at removing the allocation. We are not going to see these in the talk because we are not going to implement chaining on coroutines.
Thank you. The second question is by Ryan. If we can't use exceptions, do we just return an error code, for example, in the promise type? Does uncaught exception use compiler intrinsics?
So we are going to implement uncaught exceptions, and so you can handle the exception however you want. Let me go back to our initial function, showing how it's rewritten. Second, okay, here we are. So the body of your function is going to be written like this, and you are going to implement unhandle exceptions. So you can use exceptions. It's simply that how you propagate it back to the coroutines depends on you. The most typical thing that I saw is that the promise type has some storage where you can, when you get an unhandle exception, you store the exception there. And then you can basically, when you get the value from the task, it's going to throw the exception instead. You can look at the Folly, which is an implementation for coroutines that Facebook has, but there's also CppCon, which both use a similar method for handling exceptions.
Thank you.
So let's jump back from where we were. Okay. All right. To do this, so we were talking about transforming the body into a function, into a coroutine. To support what we want to do, we need three components. We need a task, which is the one returned by the coroutine. We need an executor, and we need a batcher. And they are going to cooperate in the following way. The task is going to be submitted to the executor, and the executor is going to resume the coroutine associated with the task. At one point, the task is going to wait on our batcher, which is the object which batches all the arguments. And once the batch is complete, it's going to execute our function and submit all of the tasks back to the executor so that they are going to be resumed. And how does it look like in code? Well, we are going to instantiate an executor. we are going to have a batcher for each of our bulk operations. Then we are going to have our coroutine, which we saw earlier the code of. And then for each user, we are going to instantiate a coroutine and call submit. Then we are going to run all the available coroutines until they are all executed. And this is what I was mentioning before, because in a for loop, we are creating multiple coroutines, the compiler is unable to remove the allocation. But in other situations where you, for example, co-awaiting a single coroutine, that happens. So let's look at our task struct. It's going to be very similar to a unique pointer, but for the handle. Like we were saying, it must have a promise type, and we are going to have a convenience type def to the coroutine handle type. Similar to unique pointer, it's going to own the coroutine handle. So it has a private field and then explicit constructor taking the handle. It's only going to be movable, so the copy constructor is deleted and the move constructor just swaps the pointers between the two tasks. And it has rise semantic. So in the destructor, if the pointer is valid, it's going to destroy the associated coroutine. Finally, we are going to have a way to expose the coroutine handle. And this is with the release method. And this is all it takes to implement our task class. Let's now look at the promise type. We'll implement all the special methods we described earlier in a minimal way. Let's start with the initial suspend. Here, we want to suspend the coroutine immediately. So we are going to call return a suspend always. Suspend always is a special awaitable which is implemented by the standard library, which always suspend. So when you call await ready, this always returns false. These allow us to suspend before starting the execution of the body of the coroutine. So we are building a lazy coroutine. Next, we are going to implement final suspend. Final suspend returns suspend never because we have nothing to do at the end of the execution of the coroutine. This, similarly to suspend always, is implemented by the standard library, and it's await ready always returns true. So it never suspends. Then we are going to implement an handle exception. Since for simplicity here, we want to ignore exceptions, we are going to call terminate. But this is normally how you would handle the exception. For example, you could use std current exception to get a pointer to the current exception and store it inside the task. Finally, we want to implement the return void, but we don't do anything with the result of our coroutine, so we can just simply leave it empty. And finally, we need to implement getReturnObject. Do you remember when we were describing the coroutine handle that there's a static method which from the promise gives us the coroutine handle? We are going to call that one to get a coroutine handle from the current promise that we are building. Once we have the handle, we can build the task, and the task is going to be returned to the caller of the function. At this point, our task is complete, and we can write the coroutine. This is going to compile successfully, and it can run. Let's look more visually what happens when the function is called. So when send email with the user is called, the compiler is going to allocate a coroutine frame. This might happen on the stack or on the heap, depends on the optimization the compiler is able to do. Then the compiler is going to create the promise type inside this coroutine frame. And it's going to call getReturnObject. This is going to create a task and initialize it with a coroutine handle pointing to the coroutine frame associated with the coroutine. Then our initial suspend is going to be called and co-awaited. And this suspends the execution immediately. So the execution goes back to the caller, and we are going to return the coroutine, the task, to our function. I see there are no questions, so I'll continue. And at this point, we implemented the task. So we need something to execute these tasks. Wait, I think there's a question.
Yes, we just got a question from Ryan. How does the compiler allocate here? Does it use global operator new?
Yes, in this specific case, it's going to use a global operator new. There's actually quite a complicated way on how coroutines can specify how they can be allocated. So you can specify the operator new for the coroutine frame. You can also provide the allocators both in the type, but also as constructor parameters to the coroutines to use specific allocators. This needs to be supported by the coroutine type. And we are not going to see specifically in this talk, but at the end, I'm going to link you to some code which actually overrides the operator new for the coroutines.
Thank you. We have another question from Jeff Erickson. How is a nested co-await handled? For example, what happens if you co-awaited something before the co-return in send email?
So in send email, we are actually awaiting something. And what happens is how I described it earlier. Like the co-await is going to be transformed in a series of await ready, suspension, await suspend, resumption, await result, resume. What actually this does, it's completely in control of the implementer of the type. So when you see co-await with an object, you kind of need to know what this object does to know what's going to happen. And in the talk, we are going to implement this method to the objects to do the operation that we want to perform. But if you were to use, for example, a different library, they would probably do something different. So the whole point is that the C++ coroutine spec basically defines some functions that once you implement, you are defining what the coroutine does. And this is quite different, at least from what I know from other languages, where the coroutine kind of comes with the default behavior. I guess with time, there's going to be some main libraries which are going to become the de facto standard, and they're going to define how the coroutines more commonly are going to be used. But there's this implementation freedom.
Thank you.
All right, so we need something to execute our tasks. So let's actually create an executor. So we're going to have a struct executor, and the executor needs to support two actions: submitting of the coroutines and executing the pending coroutines. So first of all, we need to store the pending coroutines, and we are going to use a deck for this. This is so that we have an order list, basically, of the coroutines that we want to execute. Then we want to support submitting coroutines. There are two use cases for this. There's the initial task, which is submitted to the executor, but then there's also the batch, which needs to submit all of the coroutines once it's done. Let's look at how we implement them. For the submit function, we are going to take a task, and then we are going to call the release method to steal the handle from the task. And then we are going to push it back into our deck of pending coroutines. We are also going to implement submit, taking a vector of coroutine handles. And here we are going to call the standard methods to insert at the end of the deck. Let's now look how we are going to execute the coroutines. First, we are going to implement a function, pop next coro. This returns an optional of the coroutine handle. And basically, if the coroutines, the pending coroutines are empty, so there's no pending coroutine, we are going to return an empty optional. But if there's anything in the deck, then we are going to extract its first item and return it inside the optional. Following that, we are going to implement run await available. This one is going to call pop next coro until it finds a coroutine which is not, until it consumes all of the coroutines available. And it's going to call resume on each of these coroutines. So, for example, once a coroutine which has been suspended is submitted to the executor in run available is going to resume. Note that here we can't use a for loop over all of the deck, because the deck is going to change inside the resume. And I'm going to tell you where in the later implementation. So as a summary, we implemented the toSubmit method and the method to run all the available coroutines. And our executor is complete. We now can instantiate the executor, call submit with the send email, and we saw earlier how this behaves, and run the available coroutines. At this point, nothing is going to happen because in our send email coroutine, we are just co-returning. But let's look more visually how it works. We already have the coroutine frame and the task that we saw earlier, and then we call submit. When we call submit, we move the task into the executor, and then the executor steals the coroutine handle from the task. Then in run available, the executor is going to call resume on this coroutine handle and is going to start the coroutine again. I don't see questions, but of course, feel free to ask, and we are going to stop as they come. And at this point, we implemented the task and the executor. The only thing that's left is our batch. So let's support co-await now. And this is what we want to write. We already have our coroutine from before, but now we want to be able to call co-await on the get user preferences. Co-await must be called on an awaitable object, so an object which implements all the special methods that we saw earlier. So get user preferences must return an awaitable. But our implementation, our function that we had before, was taking a vector and returning a vector. And the vector does not implement the functions needed to be awaited on. So let's create a wrapper type, the batcher. The batcher is going to intercept the calls to get user preference. It's going to store the argument, execute the function, and then resume the coroutines that have been suspended. I'll show you an example with some animations. Here we have an executor which starts with 3 coroutines which already have been submitted to it. H1, H2, and H3 means handle of coroutine 1, handle of coroutine 2, and handle of coroutine 3. The batcher also starts with a batch, which is somewhere where to store the information for the batching. So the executor is going to start executing the first coroutine, H1. H1 at one point is going to co-await on the batch and is going to be suspended into the batch. At this point, the executor is going to execute H2, which is going to go inside the batch again, and H3 is going to start. When H3 is started, it's going to go into the batch, and at this point, the batch is full, so we want to execute it. And we are going to execute it by storing the results of the batch of the function call into the batch, and submitting all the coroutines back to the executor. At this point, these coroutines are pending, and executors start executing them again. And H1 is going to call await resume, consume the result, and then complete the execution. And similar is going to happen to H2, which is going to use the result and complete. And again, H3 is going to consume the result and complete. And this is what we are going to implement now with our batcher.
We have a question, which is from Jaroszewski. Why store coroutine instead of just a parameter with the extension? It's a function description that it's a little bit long to read. If you happen to have it open, you may see it.
Yeah, I opened it. So why store coroutine instead of just a parameter? Actually, we are storing both. One is because you need to store the parameter you're going to use for the batch operation. And you also need to store the coroutine because you need to know what you need to resume, right? This coroutine, when a coroutine suspends, you're going to store the parameter. But once you execute a batch operation and you're going to get the result, you need to resume this coroutine because now this result is ready and the coroutine can use it. So you need to store both, actually. And we will see which we also need to store the result of the operation. So the coroutine can actually fetch it.
Another question just came in from Nicholas Lovell. Can we expect a standard implementation in C++23? What are currently the most stable libraries?
I don't know whether we are going to get a standard implementation for C++23. For the most stable libraries, I've been using the Folly implementation of coroutines. It has been used in production, actually, for several years at Facebook now. And it is a very good quality implementation, in my opinion. It supports everything that you want from a production code base, including, for example, stack traces of a sync operation, and it's very well done. I don't have production experience with other libraries, so I can't really make a comparison, but it has been very solid.
Thank you.
So let's look at how we want to implement our batcher. We are going to need both the input type and the return type. So the batcher is going to be a template. The batcher is going to store the executor. This is needed because we need to know where to schedule the operations once the batch has executed. We're going to store the function that we need to execute. And here you can see it takes a vector of the input type and returns a vector of the return type. And also, we are going to store whether we need to execute it. And here you see, can we take a reference to the vector type, and it returns whether we need to execute or not. Most typically, this is going to be a condition on the size of the vector. So for example, if your batch has a maximum size of, let's say, 64, you're going to return true when the batch size becomes 64, so that you execute batches of a specific size in your use case. And then we also store the current batch. So let's see how our batch looks like. And this is what we were saying earlier. We are going to store a vector with all the arguments we saw in the current batch, all the results that we are going to get, and the pending coroutines so that we can schedule them later. And this is how it's going to look. We are going to have a vector with the arguments, a vector with the results, and a vector with the coroutine handles. Now, let's look at the API of the batcher. We said that the batcher needs to be callable because it's intercepting the call to our function. And it needs to return an awaitable object because we want to call co-await on that. So we are going to implement operator call, which takes the input arguments and return the awaitable. And this is how the awaitable is going to look. It's going to have a reference to the batcher. It's going to have a shared pointer to the batch and an index inside the batch. So each awaitable represents a pending operation for our current argument. And we need the shared pointer to the batch because the batch contains the results. So as long as an awaitable is alive, we need to be able to access the batch to get the results. And we need an index to know in which of the items of the result we need to look at to fetch our result. The awaitable, so as described, it contains the batch reference, the shared pointer to the batch, and the index into which in the vector the result is gonna be placed. And we saw that we have the operator call, and now we can implement it. And the implementation is very simple. We are gonna push back into our arguments vector the argument that we just received. Then we are gonna get the index into which it has been pushed. And then we are going to create the awaitable passing the current batcher, the current batch, which is the shared pointer we were storing inside the batcher, and the index at which the result is going to be. But we were saying that awaitable needs to implement the special methods that are called by co-await when we return it. So let's do that. We can start with await ready, and await ready is simply going to call maybe execute. This is a function which is inside the batcher, and we are going to see later how it's implemented. After, we are going to call await resume, and this is a trivial function to implement. We have the batch, which we look at the index to return the value to the caller. And I think we have a question.
Yes, exactly. From an anonymous attendee. Is the Folly coroutine implementation that the speaker was referring to the github.com/Facebook/Folly/blob main Folly experimental coro? If that is.
Yeah, I opened the question. I can see the URL. Yes, it looks like that. It's inside the experimental folder. I guess the reason is because until very recently, the coroutine headers from the standard library were into the experimental folder, but yeah, it has been used in production for several years. So it's working.
We have another question from Ryan. I know this is slide code, but it looks like Batcher would need a lot of synchronization to be multi-threaded. Is this just intended for single-threaded use?
When building the slides, you need to keep a balance between the details you want to go into against the precision of the concept. In this specific case, we are looking into a single-threaded case, so there's no synchronization across threads needed. If we wanted to support multiple threads, and this will be common when you have executors, which can be thread pools, for example, you will need something synchronization. And where this happens depends a lot from your implementation. Different executors could synchronize between them, or you might have to do synchronization on the batcher. So yes, there's definitely some synchronization concerns if you're moving stuff across threads.
Thank you. The third question, or the last question that's currently open, would the standard coroutine be safe to execute with an executor that uses parallel policy and parallel unsequenced policy? Or do we need to modify anything to ensure proper memory barriers?
I think this is probably a bit of a misconception on how the coroutines work, because this standard doesn't provide any task or executor, or basically for C++20, basically anything. So there's no coroutine to be executed or on no executor. I know the standard algorithms. I have the parallel policy or the parallel unsequenced policy, but I'm not sure how they relate with coroutines. There's also the executor proposal, which is being discussed for C++23, which might provide a standardized version of executing functions. I'm not 100% up to speed with it. But the answer for now is that you will need to use a library, and what this library, the constraint of these libraries are going to be specific to the library. So you might need memory barriers, you might not, depends on the implementation.
Thank you. And another question just popped in from Samuel Guinet. Do we need to implement all this boilerplate code for every function we want to transform to a coroutine? Absolutely not.
This is the customization points for the library implementers. So a library implemented is going to offer you a coroutine library, for example, Folly, and you are going to write your code just simply returning task, calling co-await, and none of these special methods are going to be implemented by you unless you're going to go some like deep integration with your library to support it. So normal user code is not going to implement any of these. And even everything that we are showing here is actually to be able to do automatic batching. But once you have this implemented, the user code will not care about it. It will just use the batchers, the co-await, the task, and the executors, and that's it.
Thank you.
I think we have a last second question.
Right. Once C++20 coroutine is fully supported by major compilers, GCC, Clang, MSVC, would the Folly coroutine support be removed? The reason I ask is because my company uses Folly and C++17. So if we use Folly coroutines, will we have to rewrite?
This is a prediction of the future. I'm not sure. I don't think this is going to happen for the simple reason I don't think the standard is going to converge on a single coroutine library to do asynchronous programming, because it can be used in many different situations and there are different trades-offs. There's also a massive amount of code which is written in Facebook using coroutines. So I really don't expect coroutines to be removed anytime soon, at least. But again, this is my take on this. And the future, no one knows. But I highly doubt that it's going to be removed. And if ever, there's going to be a transition period similar to many library at their own optional type, and there's a migration to the standard optional, for example, now that it exists.
Thank you.
Okay, so we were seeing how we can get the result from our batch using the index simply. And then we can look into how await suspend works. So when we get the coroutine handle, we are going to push it back into the pending coroutines and return. And this is going to return the control back to the caller. And this is what is called an asynchronous transfer coroutine. But this can be made more efficient. When the coroutine is suspended, it can actually provide back to the compiler the next coroutine to execute. And the compiler will resume this coroutine automatically, doing a tail call. The next coroutine is provided by returning it. So leveraging this idea, we can change our function to actually use symmetric transfer. And symmetric transfer is when one coroutine transfers the control to another coroutine. And here we can see that again, we are putting our coroutine handle at the end of the batch, but then we are calling pop next coro on our executor, which is going to give a coroutine. And then we are going to return either the coroutine or a no-op coroutine. A no-op coroutine is a coroutine which does nothing and returns immediately to the caller. And this is one of the points where the pending coroutines are being modified in the executor during the resume of a function. So the only thing left is to implement maybe execute. And this is very simple. We are going to check whether we need to execute the batch. And if we don't have to execute the batch, we are going to return false. Then we are going to call our operation and store it inside the result. And since we perform the operation, we are going to submit all the pending coroutines inside the executor to be resumed. Then we are going to create a new batch. So the next calls to the batcher are going to start from an empty batch and return true. And this means that the maybe executed, so whoever called it, it's ready to continue. And at this point, the batcher is complete. We're going to be able to instantiate the executor, create a batcher with the user as an input type and user preferences as an output type, give it a name, and then instantiate it with the executor. Our function, this is the function which takes a vector of users and returns a vector of user preferences. And size equal is simply a lambda, which returns true if the size of the vector is equal to 10. So here we are saying that we want a batch size of 10. Then we are going to have our coroutine, which is going to call coawait on our batcher, passing the user ID. Let's see how this works with a visual representation. Again, here, notice we have the executing block, which tells us what is currently executing, and take a look at the stack, which is going to show which functions are being called. Again, we start with the 3 coroutines at the start in the executor. So initially, we are going to call run available on executor, and we are going to start the first coroutine in the pending coroutines. And this is going to start executing. It's going to call at one point the operator call on the batcher. And the operator call in the batcher is going to store the argument inside the batch. Then it's going to return the awaitable. The compiler is going to call await ready on the awaitable. And the await ready is going to call maybe execute. Since we only have one item, maybe execute is going to return false. And await ready is also returning false. At this point, it means that the compiler is suspending H1. It's going to call await suspend, which the current handle, which is going to store the handle inside the batch, and then it's going to call pop next coro. The next coro is H2. So await suspend is going to return H2. And at this point, the compiler is going to automatically resume H2, which is going to start executing. And similarly, it's going to call operator call, store the argument, get the awaitable, call await ready, maybe execute, return false because the batch is not ready. So suspend by storing the batch, calling pop next coro is going to get H3, and this again is going to start resumption. Now, when H3 calls the operator call, it's going to store the argument. And here we assume a batch has a max size of 3. So at this point, is going to return available, and we are going to call await ready. Await ready calls maybe execute. And this time, the size of the batch is correct. So we are going to call our operation. When we call the operation, we are going to get the results, and the two coroutines are going to be moved into the executor. H3 at this point, maybe execute at this point, returned true. So await ready returns true, which means the coroutine is already, like the awaitable is ready. So there's no need to suspend. H3 is going to call await resume to get the result, and then is going to resume from where it's suspended and complete. At this point, run available, which was at the bottom of our task, is going to pop the next coro from its pending coroutines. And the next coro is H1. So it's going to call resume. H1 is going to start, call await resume, because it's been resumed after co-await, consume the result, and then terminate. And similarly, again, run available is going to call resume on H2, which is going to call await resume, get the result, complete, and terminate. And at this point, when the last instance of the awaitable is gone, which is after the resumption of H2, then the batch, which had the shared pointer, is gone as well, and we free the memory. At this point, we completed all the implementation of the task, the executor, and the batcher.
We have one open question from Ninat Mixa. What happens if we don't have enough tasks to fill the batch? Is it going to wait indefinitely, or should we implement some timeout mechanism? How did you solve that issue in your production?
This is a great question, and actually we are going to look at it now.
Thank you.
So let's put all of these together. As we were saying, we have the executor. We create a batcher for each of the various operations, and then we have our coroutine. Our coroutine is going to call co-await on our batchers, and we saw that they are going to store the items inside the batch, and then continue with the execution. Then for each user, we are going to create a coroutine and submit it to the executor. And then we are going to run all the available coroutines. But what if we finish the available coroutines before we completed all the tasks? An example, like Nina was saying, is the batch has no limit, because maybe there's no maximum limit for your batch, or the limit is not a perfect divisor of the vector of operations. So for example, you have 5 users, but your batch maximum size is 4. So let's look how it is. Let's see how it looks like. We have H1, which goes into batch, and H2 that goes into the batch. At this point, we assume the batch has size 2. So it's executed immediately. H2 consumes the result and continues. At this point, the batch has completed, and H3 is stored inside the batch. So the result is that the executor has no pending coroutines, and the batch has pending coroutines, and some tasks did not complete. We are going to solve this by forcing the execution of the task. So we're going to have a Boolean parameter we can call to maybe execute. But when do we stop calling force? At one point, we will have executed everything. We stop when all the tasks have completed. So we need to know which task have completed. For doing this, we are going to have a counter inside our executor. And when the tasks start, we are going to increment this counter. We're also going to pass a pointer to this counter to our promise type. In our promise type, we have the pointer to the counter. And when we complete, so we change return void, we're going to return -1. Finally, we are going to use the available change run available to actually return whether we executed all the tasks. And we can change our logic to be a while loop with the user preference, which force the execution. I see there's a question, but maybe we can move it to the Q&A in the Gather Town later, so we can get to finish. We are very close to the end. But here we are calling maybe execute to match, because once you force execution on one batch, you might unblock some coroutines that then are going to fill the batches of the other coroutines. So we can change this by calling not returning false if the batch is empty, and then using the short circuiting to make sure that maybe execute only of the first batch is executed. And we can see that similar to before, once we have H3 left, we can call force execution to resume the coroutine and end. And this is basically how we're going to implement everything. Run to completion is going to simply call read available in a while loop, and then use the or short circuiting operation to call the first maybe execute of the thing. We are quite close on time, so again, I'll skip. I see there are some questions. I'm very happy to take them at the end of the talk. Let's look at the benchmark of what we implemented. We wanted to automatically implement batch our operation. So how does it compare to our solution? This is the solution we saw initially with the manual batching done with the algorithm implementation. And this is how it works with our Coro batching. The size of the code is very similar, but we can see that the logic translates almost one-to-one. Also, the boilerplate that is at the bottom and at the start, it's quite fixed. So if the logic inside the coroutine grows, the complexity of the code around it would not grow much. Maybe we would have to create a new batcher if we have a new batch operation. So this gives us a good win on the readability side. But how are the performances? So I ran the same simulation as I described earlier with 10 milliseconds per call and the 50 milliseconds per delay per item with 100 user and 50 millisecond. And we can see the Coro batch actually is faster than manual batching. This is very surprising, and it's not expected at all. The reason why this is happening is because the manual batching is not calling reserve on the vector to allocate the memory ahead. If you do that, Coro batching and the manual batching has the same performance. And similar performance is also obtained using the ranges implementation. All of these are going to be in the code that is linked at the end. But let's try a simulation without overhead. We put a very high cost to calling the function, but what if the function were not? This is the simulation without delays, and we can see that manual batching is still fastest, as we expected, and manual batching is slower. But Coro batching is almost 3 times as slow. This is very slow. Well, the thing to notice is actually here the unit is nanoseconds, and here we are talking about 200 extra nanoseconds per item. Depending on your use case, this might not matter at all. But the other aspect is that actually our implementation is quite naive. It has many indirections like shared pointers, it allocates coroutines, which slow it down. And we can reduce them with additional customization points that the standard provides. And this is what is called Coro batching optimized. And we can see that we get to 20% from the baseline implementation. And so you can get very close to it. And again, depends on your use cases, whether this is fine or not. We are not going to see how to get to the optimized version, but the code is present in the link at the end. So in conclusion, we saw a new point in the performance reliability trade-off with coroutines. We learned the main customization points for coroutines, and we saw that coroutines can be used for more than just async programming. Coroutines are also powerful, but at times are a bit complicated to understand. Again, you can find the full implementation at the link above, and there's a library which I implemented to expose the concepts in a bit of a higher level API, although it doesn't implement the latest version of the idea. And with this, we covered all. So thank you very much for listening to me today.
Thank you, Francesco. I suggest the questions are best taken to GatherTown at this point because the session time has been finished. I've copied the open questions and we'll share them in Discord so you can take them there. Thank you very much.
Perfect. Thank you. Bye.